Okay, welcome to this week. We're talking about sound. Go ahead and get started by taking out your Cornell notebook, starting a new page with the topic of sound. And this learning target, I can describe changes in wave properties, movements, and interactions as they pertain to sound. Before we really dive into this, I do want to mention that at the end of this are the assignments for this week, and there's a change to the way we're doing assignments for the remainder of this quarter. You're going to have one required assignment and one extra credit assignment. So just make sure you are doing the required assignment, and if you want to do the extra credit, you can go ahead and do that, but I'll talk about it at the end as well. So first off, let's talk about what sound waves look like. At the top here, we can see that we have air molecules. And whenever a sound is made when you speak, you are vibrating the air molecules so that they oscillate back and forth. And when they do that, there's going to be areas where there's low pressure as far as less air molecules. And then there's going to be areas of high pressure where there's a lot of air molecules all bunched up. And that wave is going to travel in this direction. So the air molecules are not moving through the air all the way to the other person's ear, whoever's listening. What's happening is these air molecules are oscillating back and forth in space. And when they oscillate back and forth in space, they're going to create these areas of low pressure and then these areas of high pressure. This type of wave is going to be a compression wave. What we've been looking at are transverse waves, the waves that look like this. And we can actually graph the longitudinal wave or the compression wave using a transverse wave, where all the crests represent high pressure and all the troughs represent low pressure. So when we graph it doing a transverse wave, it does show up just like the waves that we've been seeing, and we can go ahead and measure wavelength and every amplitude and everything like that using our transverse wave instead. This is just a different visual representation. The dark area represents area of high pressure. Light area represents an area of low pressure, so that's the same as this area. The dark area is the same as this area. And again, you see that the really dark area lines up with a crest and the really light area lines up with a trough. What we call these in sound waves is that this is a compression where they're all bunched up, and this is a rarefaction where they are all spread out. Okay, so some properties that you need to know is that air molecules move back and forth, compressing and decompressing. The air molecules do not travel all the way from the source of sound to the ear. Instead, the energy of the wave hitting your ear creates the sound. If it was the movement of the actual air molecules all the way across, that's more like wind, where the air molecules are moving all the way across an open area. There's no sound in a vacuum, so in space, there's not going to be any sound because there's no medium for the sound waves to travel through. It has to have either a solid, liquid, or gas. In space, there's none of those, so sound can't travel in space. The amplitude of the wave is going to represent how loud that sound is going to be. It's the density of the compressions. And then decreasing the period or increasing the frequency is going to change the pitch of the sound. So a higher frequency sound, the more waves that go by in a given second, the higher the pitch is going to be. The speed of sound is in non-humid air at 20 degrees Celsius. I know that's very specific, but there's a reason for that. The speed of sound is 343 meters per second or 767 miles per hour. So the speed of sound is constant for any medium, and there's ways of changing the speed of sound, but you have to change the medium. You can't change it by changing the amplitude or the frequency. The only thing that changes with amplitude and frequency is how loud or soft the sound is and how high-pitched or low-pitched the sound is. So then our equation of a wave here, you can see the velocity of sound, if that's given in an area, or if we know the speed of sound and we're given a wavelength, we can figure out what frequency it is. So our equation of a wave is our velocity, speed of sound, is equal to our wavelength times our frequency. All right, we'll be back for the next part in just a moment.